afternoon, everyone, and welcome back once more. Today we've got a whole new sophisticated setup. That's for you people on Zoom and for those of you watching the recording. So please bear with us if there are technical difficulties, which given our track record for the class so far, I'm sure there will be. Last class we left off talking about analysis of different search algorithms. We looked at the code for binary search, evaluated its runtime, and now we're finally at the point where we can actually look at the code for it. The student representative survey, the SSLC survey, is now available for all of you to answer. Please provide feedback. This is the way that I can ensure that we actually make the changes that you want to see in the class. We won't always agree with all the changes you recommend, but please know that each and every comment that you provide to us will be taken both seriously and discussed among the teaching staff to see if we can make changes that benefit you in the future. So please, 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 if I can ask you for one thing this week, it's fill out that survey, give us some positive feedback, give us some constructive feedback, and help to make foundations of algorithms better, both for you and for the iterations that follow. So now, thankfully, I managed to get our code up on screen, and we have our code for binary search. Now, we're going to run through this a little quickly because we've already spent a lot of time for binary search, but we will point out a few key features of the algorithm. As usual, we have our function prototype, but you'll notice above it we have two hash defines. These hash defines are going to be our true and false values for binary search. Remember that older versions of C don't natively have true and false, so we're going to use hash defines to communicate these values to a reader who might not necessarily know what we, as coders of the particular function, intend by zero or non-zero values. Much, much clearer if you can tell the user through a hash define which values we're allocating in our function for success and which values we're allocating for failure. Given that we also haven't discovered how to do variable-sized arrays and do dynamic memory allocation, we're going to set a cap on how large our arrays are going to be in which we do binary search. I'm going to skip out this function here. We'll come back to it in just a minute. Let's look at our main function. We create an array of size called A, and we fill it up with some stuff. And then we do a binary search. And now let's actually look at the binary search function itself. So as before, we have a variable for setting the, yes?
It's just, the screen's a bit hard to see.
Screen's a bit hard to see?
Yeah, it's like very pale. Yeah, much better.
That'll be a bit better. Then you don't see me, but we'll deal with it. Liam, make sure that we still have adequate video quality there.
Looks really good.
Okay, all good. So as we saw in our pseudocode version of the algorithm, we're going to need to create a variable to store the midpoint of the array. This is our value mid here, and an outcome that will store where, if we find the value we're looking for, where that value is. Here we have our one of our assertions, except this time instead of coding it as an assertion, we have it coded as a standard if statement with a return not found. It's playing kind of the same role here, except you'll notice that we also have this recursive call going on twice in here. So not only is this playing the role of an assertion, it's also doing something important for us. It's performing our base case. So we know if we're bringing up the two sides, we know it's not in that side, no it's not in that side, and we're slowly narrowing it down to a certain portion of the array. If the bits of the array that we're throwing out match, then we know that the item is not in there. It's neither in the portion to the left that we've thrown out, it's not the portion to the right we've thrown out, and the left and right portions have now met in the middle, and so it's not anywhere in the array. Great. Now we take our midpoint, this is exactly as it was in the pseudocode, and we check to see is the element we're looking for bigger than or smaller than the item we're currently looking at. And the way we do this is through this mysterious CMP function that I skipped over earlier. So to the CMP function, we're passing two things. We're passing one thing to compare and a second thing to compare. Remember, in our binary search algorithm, we want to compare the item we're looking at to the item we want to find. And so these are the two things we're passing in. Now let's see how the CMP function works. The CMP function is taking in two data T types. Does anyone have an idea why we might use this weird data T type instead of a normal specified type like an int or a float? Why might we have type def this? And Liam, can I have the Roman?
Yeah, you're cool. It's not on though.
Yeah. So if I want to put integers in my array, then I would have to specify int in the CMP function. What if I wanted to check floats? Then I'd have to put floats in there. Why might, instead of using those types, I've used my own custom type, data_t. What might this allow us to do? Knowing ahead of time that I'm going to want to compare a bunch of different types. Yeah.
You can sort of just change all the types at once with the type def instead of having to try and find every single data type.
Yeah, so you're not coming through our room microphone, but because, I'll repeat the answer for everyone. The reason why we might want to do this is because if we want to switch out the type that we have in our array quickly, using a type def allows us to very quickly swap all instances of data t with the thing that it's representing. So if we set data t to actually be a float, then every time we use data t, we'll actually be using floats. Likewise, if we want to change our mind and then make it so that we're comparing ints and storing ints in our array, if we make data t an int, then every time we use data t, we'll have an int there. So our CMP function is now very, very simple. It's just taking the difference between the two types. Calculating the difference between the two types will result in a positive number if our first number is bigger than our second. It will result in a negative value if the second number is bigger than first, and it will result in 0 if the two are the same. In this way, it gives us the ability to quickly and easily tell whether something is larger than, smaller than, or equal to we can stop caring about the exact number that it returns. All we want to know is it positive, is it negative, or is it 0? And so CMP functions are a very common pattern that essentially perform this operation. We're going to throw away the actual value of the difference, and we're going to care about the sign of the difference. And the way we do that is by checking, is the output from the CMP function less than 0, bigger than 0, or equal to 0? And that's going to happen in our else statement. Is if it's neither less than 0 nor bigger than 0, it must be equal. There are only 3 options. Then we have our recursive call to binary search, which happens in both the branches. And if neither of those branches were taken, again, that means the two values x1 and x2 that were fed into CMP were equal, which means the item that we're currently looking at and the item that we were looking for are the same thing. And so we found the item that we were searching for in the first place, and our binary search is done. You'll also notice a few other interesting features of this function. The first is that we're using a pointer to a value location here. Why might we use a pointer? We already know the use of pointers. So if we're passing in a pointer to some integer called location, and we're using that to as one of the outputs from our binary search function, why would we make this a pointer and not just an integer? Tarish, do you have an idea? Nope. Anyone else?
Sorry.
Okay, Xinjiang, you're up again.
If we pass it as a pointer, we could change the underlying value after the function exits, and the return value of the function could be used for other purpose.
Exactly. If you'll notice in this function, we're returning a value found or not found. However, we want to know multiple things as a result of the output for this function. We don't only want to know is the value in the array. We want to know where in the array is it located if it was found. And to do this, we can use a pointer that is the value that it's pointing to of which is modified inside the binary search function. So this allows our function to return found or not found while still giving the main function back a value inside a pointer that it can actually use. So if we go back to our main function, we'll see that when we call binary search, we're calling it with the address of an integer, and inside binary search, if we find the item we're looking for, inside that integer that belongs to the main function, we're going to store the location of the variable that we've found. Let's give this a run, just to confirm that it works. You can see here the output that we expect. If the number that we're searching for is, where do I have it over here? The value that we're searching for is a counter variable that's going from 0 to 5. The contents of the variable are 2 by I plus 1, so we can print that out super quickly if we want to see what the array looks like. Not sure why that didn't work and print our array. Didn't save it, that's why. I is initialized further up. There we go. And that's out of space.
Nice.
So we can see that our array contains all these numbers. 0 is not in A. 1 is in the first place. 2 is not in A. 3 is in A1. And can people see the pattern that's coming across with the numbers in the array? 1, 3, 5, 7, 9. That should be familiar to all of you. Our array is, of course, just printing the even numbers. And you can tell that binary search is working because it's returning it's returning yes for all the even numbers and no for all the odd numbers and printing out the according positions. Okay, now we are done with our binary search for the time being. However, we still have this looming question. Oh, we'll get back to that in a second. Which was, how in the first place did we get a sorted array? Remember, binary search only works on sorted arrays. But before we turn to that, I did have an extra video for fun for you. You'll remember that last lecture, we talked a little bit about Matt Blaze's Great Binary Search Challenge. And here is Matt Blaze on John Oliver.
By the way, is there a more 90s series of words than a hacker named Matt Blaze? It's got to be right up there with talk to the hand, Furby. And
so indeed, there is nothing more 90s than a hacker named Matt Blaze, and there is nothing more 90s than learning about Quicksort from a hacker born in the 90s. So how do we get a sorted array in the first place? Well, we could use insertion sort, but we're already well aware of some of the problems with insertion sort. It was a little slow, the runtime wasn't great. Can we do any better? Well, insertion sort, if we actually calculate it out, gives us average time of n squared. We have this nice little series. Remember, our C is the number of steps that any given operation takes, the amount of time that any given operation takes. So we have O of n squared for our insertion sort, but quadratic time really isn't so good. So we want to find a better algorithm. Well, it turns out that we really can. And this introduces our module on Quicksort. Quicksort is one of the most widely used sorting algorithms. It's been part of the C standard libraries for quite a long time, though now the actual sorting algorithm that is most commonly used in C, I think, is a modification of something called tin sort by memory. Liam, do you know the answer to that one?
Not in C, but in general, yeah. Java and Python.
Anyway, so Quicksort is one of the fastest sorting algorithms available, and we're going to learn about it. This allows us to improve on the average case for our sorted input, which is really what we're after. If we don't know what kind of input we get, which is going to be the case for many of our applications, we want our default library to have a sorting algorithm that functions pretty well no matter what the input is, or at least on average. So the key concept behind Quicksort is this idea of making incremental process across the array through recursive calls, dividing it up into sections, sorting each section, and then combining the sections. This will be a recurring pattern in a number of different algorithms that both we've already seen and that we will see. It's similar in form to binary search in that each time we are making our problem size smaller and smaller and smaller until we get something that's very easy to solve. In the case of binary search, it's for an array of size 1, can you find if the element you're looking for is in there? And it's a similar idea for our quicksort algorithm. It's for an array of size 1, can you sort it in the correct order? Well, yes, obviously, we know how to sort an array of size 1. You just return it straight away. So let's dig into this with a demo that actually steps through Quicksort before looking at the code. This should help you build the intuition so that when we come to the code, it'll be easier. On the right here, we do have the pseudocode for Quicksort, and we will follow along somewhat with the pseudocode. But the key thing to watch is actually the operations that we're going to perform on our array over here, because they'll probably make more sense and that pseudocode will become clearer once you already understand the algorithm. So the first thing for us to do is to pick a pivot. While we're learning about Quicksort, let's just pick the pivot. This is going to be our special element, which we'll see how it works. Let's just pick the first element to be the pivot. Now what we want to do is we want to figure out which of the elements in our array are smaller than the pivot and which elements are larger than the pivot. So I've already color-coded for us which ones are smaller, which ones are bigger. There's one element that's the same as our pivot. There is one, and then after that we have another one that's smaller and then some bigger elements again. Now what our goal is to rearrange this array such that all the smaller elements are on that side, all the bigger elements are on that side, and then our pivot and any elements that are the same are in the middle. So this is going to be fulfilling our idea of chunking the array into different parts that we then can solve individually. So there I've reordered them, and for the time being, let's just assume that we have a magic function called partition that does this operation. So we've chosen a pivot, we call our partition function, and now we've divided up our elements on either side of the pivot. Let's look at our pseudocode quickly. You'll see over here, we choose a pivot. You should be able to see that red dot. We choose a pivot, we then call partition, and now we run Quicksort on the side that's smaller than the pivot, and we run Quicksort on the side that's larger than the pivot, and the bit in the middle is already sorted because that is our pivot itself. You'll also notice that if, in our base case, if n is less than or equal to 1, we just return. So now let's run Quicksort on everything to the left side of the pivot. This is our three numbers 6, 19, and 12. Let's run our algorithm again. Choose the first element as our new pivot, so we'll call this pivot prime. Then we call partition and put the elements in the right order on either side of this pivot. So 2 is now smaller than pivot prime. 12 is smaller than pivot prime, 19 is larger than pivot prime, and 16 is the pivot itself. And now we do our recursive call again. So run Quicksort on the left-hand side of this. Well, the left-hand side is only a single element, so it's already sorted. Which means that we're at our statement here, if n is less than or equal to 1. The length of the array is only 1, so we just return. That's done. The element 16 is the pivot, is pivot prime, so we don't touch it. And we run Quicksort on the other side. Now the other side is the number 19. There's only one element, so again, that's our base case, we're sorted. Now what we have is the sorted chunk that we were talking about. Well, we've just finished all the elements on the left-hand side of our normal pivot. So now what do? We move to the right-hand side. This is our second call, and it's going to operate on these elements here. So we do the same thing over again. Create a new pivot. We can call this pivot double prime, but this is just inside a function call, so we can use the same variable name really. There's our pivot double prime. We have 27 and 38 that are smaller, so our partition function will put them on one side, and our value 89 that is larger, so we're going to put that on the other side. We've run our partition function, we get our results here with pivot double prime over here, our smallers and our largers. We have our recursive call on the left-hand side. We choose 27 as the pivot, 38 is larger. That gives us the elements in the same order they were before. But 38 is only a single element, so when we run Quicksort on it, we just return it straight away. Which means that these two elements are sorted. Now we run Quicksort on the right-hand side. Of course, the right-hand side is only one element again. And so that Quicksort call also terminates very, very quickly. Now we're at the point where we have done Quicksort on the left, we've done Quicksort on the right. We have our pivot in the middle. Is our array sorted? We have no more Quicksort calls to go. We have finished our round of Quicksort. So if we go back to our slides, we can see that the way this was working was by picking a pivot point. In this case, the pivot is going to be in this graphic in the middle, that equal sign. I think this graphic is in the book. And then what we do is we have this two lumpy sets of arrays. We run Quicksort recursively on both of those lumps, and assuming that they come back sorted, then we can put those lumps together with the pivot in the middle, and we're done. I'll jump through all of these, because this was just in case the iPad wasn't working. And now we're ready for a correctness proof of Quicksort. Quicksort is often treated as quite a confusing algorithm, but you can see if you actually step through it, it's not that difficult. The key thing to note is combining the smaller and smaller quicksorts on the smaller versions of the problem. Remember, that's how recursive functions work. You have your big problem, you find how would this work if we could assume that a smaller version of the problem came back solved, and then come up with a strategy for solving the smallest version of the problem. In this case, the smallest version of the problem being when n equals 1, you've already got a sorted array. So for our correctness proof, as usual, we need an invariant. In this case, our invariant is going to be that we have some invariant r, and we have two variables that keep track of each side of the array. Where does the unsorted left-hand side begin, and where does the unsorted right-hand side begin? And these are going to be our FE and FG, and as usual, they're going to be bounded between 0 and the size of the array. For a given pivot value P, we then want to be assured that all the values in the smaller half are in fact smaller, so that's everything between 0 and FE minus 1, that everything in the middle, that is between FE and FG, are equal to the pivot, and everything to the right of the pivot is bigger. This is just the same as the same thing we were doing, only more formal notation for talking about it. So the translation is both sides on either side of the pivot, you're still in the array. Everything on the left is smaller, everything in the middle is equal, everything on the right is larger. Now we have our function, just like the pseudocode we saw in the iPad demo. The key thing that I want to point out here is the new assertion statements that we've added into our pseudocode. So choose the pivot, then we're guaranteed that n is larger than 1 because we have already passed this statement, if n is less than or equal to 1 return. So we know we have more than one element. And because we have more than one element, we know that the first line of this assertion is correct. And we also know that the pivot is somewhere in the array by definition because we just chose the pivot to be the first element. Now we run our partition function and we assert our statement again. And assuming that the partition function is correct, and we'll get to the proof of the partition function in a minute, our full assertion, the big statement that we made just on the other slide, should be correct because of the definition of the partition function. So assuming we have a correct partition function, this should work out because this is exactly what the partition function does. Then we have our two recursive calls, and now we have, again, a new assertion. Our assertion is that everything on the left-hand side of the pivot should be sorted, and everything on the right-hand side of the pivot should be sorted by our definition of what Quicksort does, which gives us, by implication, that the entire array is sorted, because we know that everything on the left was smaller, everything on the right is greater, and if everything smaller is sorted, and everything greater is sorted, and everything where we are is equal, we've completed our proof because there is no way for any element to be out of place in our overall array. Now we just have to define the partition function because, of course, our proof doesn't work if our assertion R is incorrect and if our partition function isn't actually doing this thing of dividing things up on either side of the pivot correctly. Partition works as we saw. It permutes the elements of A into the smaller section, the equal section, and the larger section. And for the purposes of actually writing code, we're also going to want it to return FE and FG, that is, the boundaries of the sections. We need to know where the smaller half begins and where the larger half begins in the array in order to continue our algorithm. So let's turn back to the iPad and check out our partition function. This is probably the most complicated of Quicksort to understand or to actually get right when coding it is the partition function. The rest of the code is actually quite simple when you take a go at it. So here's our partition function on the iPad. As before, we're going to have our pivot element that we've selected, and in this case, we're going to pay attention to two things, both to the index of the pivot, which is 0 right now, and the value of the pivot, which is going to be 26. Let's go through this code step by step to actually see how it works. So the first thing we have to do is to initialize our three values, next, FE, and FG. Next is going to be the index of the item that we're currently looking at. So we're going to be going through the different elements, figuring out which are smaller, which are bigger, and we need some variable next to tell us which is the actual one we're looking at. So let's set that to 0. Do over here, next equals 0, and that's going to be pointing to the pivot at the start. I might move that up a little. In fact, I'm going to put next up there for the time being. Next. Now we also set FE to 0 because we don't have a smaller half yet. But one thing I want to point out is the way we use FE is as a boundary. So because FE is 0, we're actually going to put our boundary marker there on the left side of the 0. You'll remember that if we go back to the actual Quicksort code, we're using FE and FG -1 in various cases. This is to allow us to point to the place on one particular side of the boundary, because of course it's a boundary, so you have to determine whether the element that you're currently talking about is included or excluded from that. And in this case, we're going to exclude it. And FG, we're going to set to the other side. This will be FG over here. Now, the reason why I've chosen to be exclusive with respect to the boundary is because we don't have a place for the items that are larger and smaller yet. We don't currently have a section. We don't have any items in that section. We don't have any items in this section. All we have is a section of items that are not yet prepared. Once we get items that are prepared, we're going to move FE and FG through our array to make room for them. And we'll see how this functions in just a moment. So while next is lower than FG, so while we still have items that haven't been partitioned yet, we're going to move our value next along and along and along and along until we hit the boundary of the items that are larger. And we're going to keep next in between our two boundaries. We're going to keep it in between the side that's smaller and in between the side that's bigger, and everything left in the middle is the items we're still not finished with. So if while next is less than FG, so while we're still going along, if the current item that we're looking at is less than the pivot, so that's our statement over here, if everyone can see, if A next is less than the pivot, swap the item that's currently at FE with the item that's next, and then increment FE. Otherwise, if the current item that we're looking for is bigger than the pivot, swap the current item, which is A next, with FG -1. So that'll be the element that's currently in the last position, and then move the boundary up. Let's actually run this to see how it works, rather than just talking about it, because it'll make it much clearer. So let me just get the pen out again. And looking at, and there's no else statement there. So I need to write my else statement in so that all of you know what that is.
What does FE and FG stands for? What does FE and FG stand for?
Greater, first, equal.
First greater and first equal. Thank you, Liam. Okay, and we need our else statement, else next plus plus. So if we're looking at an item that's equal to the pivot, just keep moving along. Now let's actually run this. The first item that we're looking at, and I'm going to have Zoomies, you'll type this in chat, everyone in the room just yell it out, which of the branches I'm in. So the first item that I'm looking at is it equal to the pivot, is next equal to the pivot. You can yell louder than that.
Yes.
Come on, I need to hear it a bit louder.
Yes.
Yes, great. Okay, so we're in our last branch over here, and we move next up by 1. Move next up by 1. Now next is pointing over here. We're still less than FG, so we're still in the loop. Are we less than or bigger than the pivot? Everyone. We're less than the pivot, so we swap FE with next. So swap FE and next. What were those values? Liam, do you remember what the values were? Deleted them now, I don't remember. 26 and 16.
Well done.
So we've swapped them. That is still our value P, and maybe I'll write that over here. So we know for the rest of the time. P is 26. And now what we do is we move up our boundary and move up our next. So our next is now pointing here. It's at the third element along. And we've moved up our FE boundary. And our FE boundary is now here. And now all of this is part of FE. So that is the part of the array that is smaller than the pivot. Now we are looking at 19. 19 less than 26, yes or no?
Yes.
Yes, less than 26, so we do the same thing. We do a switcheroo. And we move up the boundary by 1. And now both 16 and 19 are on the smaller side. And we also move next up by 1. So we're looking at the next element again. We do this another time. I'm not going to ask you again. We move, I just rewrote them, 12 and 26. We move up our boundary. It's FE there now. And we move up our next. And now finally we've got something a bit different. So 74, bigger than or smaller than 26?
Bigger.
Bigger. Okay, so now we're in our other branch. Let's see what happens. Swap next with the element on the left side of the FG boundary, of the first greater boundary. So let's do that swap. We're swapping 74 and 89. And now we move the boundary of the upper part down. So first greater now includes this part. So you can see that as the partition function runs, the first greater boundary is going to move from the right somewhat towards the middle, depending on how many larger items there are. And the first equals is going to move from the left-hand side up, depending on how many smaller items there are, until eventually they meet in the middle and partition is done. Now you'll notice when we found a greater item, we're not moving our next up. This is because we just swapped a new item into the next position that we now have to evaluate. So what previously was at this position was 72, and that was the item we compared. But we haven't actually done an analysis of what 89 is compared with 26 yet, and so we don't move our next pointer up, we just keep looking at the same item. However, we know that it'll still terminate because once we look at this item, we will either swap it to the end, swap it to the beginning, or if it's equal, we'll just move it up. So let's do this again. 89 is bigger than 26. We swap it with the thing on the left-hand side of the first greater boundary. Move our first greater boundary, and that was 18, if I'm believing correctly. And now we've only got a few numbers left. Now 18 is no longer bigger than, so we're going to go back to our first if condition. If the element that we're currently looking at is less than the pivot, swap next with FE, which is now over here. 26 and 18, swap. So it's still, 18, 26. move up our boundary, and now we do move up next this time. And if we complete this process very quickly, I think that was right. Oh, yep, so 27 gets swapped into there. That becomes 26. And now we're at our condition where the two of them are equal. So we're in the last branch of the if statement. The two of them are equal to each other, and so we just move next up by another one. So next is now at 38, but at the same time, our FG is over here. And so when we finally finish this, our FG and FE have, our next pointer is no longer smaller than FG, and so we're unable to continue in the while loop, but that's okay, because now we have the state of affairs where everything to the left side is smaller, everything to the right side is bigger, and everything in the middle is equal. Our partition function has completed successfully. Now you can see that when drawing this out by hand, it's easy to make mistakes, but if you do it slowly and methodically on an example like this, you'll probably find that it's actually not too bad in order to figure out how this is working. The main intuition to get is the movement of these two barriers, first equal and first greater, to progressively narrow off the parts of the array that are smaller than, greater than, or equal to the pivot. And joy of joys for all of you, I'm sure, this means we are now ready for the proof of our partition function. Thankfully, now that you've seen a few of these, they should start to become more intuitive. We have, as before, a condition ensuring that all our variables are within the bounds of the array, so both next, first equal, and first greater should all be within the array. Everything to the left side should be of the pivot, and the barrier should be smaller. Everything that's equal, that's on the other side of the lower barrier, first equal, should be equal. And everything that's larger than the first greater barrier should be larger. And we don't actually say anything about the elements that are, we're not going to say anything about the elements that we haven't looked at yet. So here's our initialization. Let's have set up our barriers, set up our next pointer, and assert that our statement is true. Now we enter our while loop, and we assert two things. Firstly, we assert our regular loop invariant, and we also assert the extra condition of the loop. Remember, this is our pattern. We take the invariant that we have for our entire function and combine it with an invariant that's specific to our loop. In this case, our loop termination condition next is less than FG. We do our operations to check if the item is less than, and if it is, we should, after moving everything up, it should still be the case that we haven't violated our condition, that everything on the left side of the barrier is smaller, everything on the right-hand side of the barrier, and everything in the middle is equal. Everything equivalent to the pivot is equal. This should not surprise us because, as we just showed through our demonstration, the impact of this swapping should be to ensure that the current element that we're looking at doesn't violate the invariant, and then to move up the boundaries appropriately. In our second branch over here, we're doing the same thing, just for the other side. If the element was larger, in order to ensure that we don't violate the invariant when we move next up and when we move the barriers around, we need to do the swap. And doing the swap and moving the barriers ensures that we're still compliant with our invariant. In our third branch of the loop, we do the same thing as well, only this time because we're not swapping elements around, we don't need to do our swap because we're equivalent to the pivot, so we're just moving on. At the end of this whole process, we can assert that the invariant is still true because in each of the possible branches our invariant were true, and so there's no point within our program at which the invariant could be made false up to this point. But we also have some extra things we can say. we can say that next is now greater than or equal to fg. Why can we say that? Well, look at our loop termination condition. Our loop only would have terminated if next was greater than or equal to fg. So we know that that's true. And we also know that fe, first equal, is less than next because that was our condition for next is definitely at the pivot or larger. So we know that the smaller side is going to be to the left of next, which combined all together gives us our final proof that the entire thing is partitioned in the correct manner. Because we know that everything to the left side is smaller, everything to the last side is greater, everything in the middle is equal, and we've set our boundaries such that they touch except for the elements that are equal. So we're done. We also want to know not just is our algorithm correct, but is it efficient? And so we have to determine how many times we're actually going to have to go through and compare different elements in the array in order to complete partition. Well, let's assume that we let some variable t be the difference between the element that we are currently looking at, our next variable, and our first greater than, which we know must be a maximum of the length of the array. This gives us our initial value for t, we'll call that t0, which is n, because next starts at the 0th element, and fg starts at the last element, so the difference between the last and the first is the length of the array, which is n. Then at each iteration, if we look at our code, we know that we're always either moving up to look at the next item, or we've swapped something into the current item's position. So in each iteration, we are going to reduce the size of the current t by 1. The loop ends when t gets to 0, because that's when there is nothing more to look at, which means there are fewer than n iterations. As a result, we know our partition function is O of n, because if t starts at n and goes down by 1 each time, the amount of times you can decrease it by 1 until you get to 0 is n. This allows us to build a proof of what the runtime of Quicksort itself is. If we count up the number of steps required, let's go back to our Quicksort code. Okay, so in Quicksort itself, we have 2 recursive calls, which means, and each recursive call is going to operate on a maximum of, on half the array. And because we have 2 of these, and we have n steps in the middle, this is going to give us a runtime of n log n. We're not going to do the proof, but you can get to it through a recursion relationship. In the worst case, however, Quicksort is still n squared, because this is only in the best case where our 2 halves of our array, the bigger half, the half that's smaller than the pivot, and the half that's larger than the pivot are equal. So we had a hidden assumption in this statement, which is that Quicksort is actually going to split it evenly half the time. Like in our picture of how Quicksort worked in the schematic picture, we had it that the left half and the right half, the bigger half and the smaller half were equal. But that's not always going to be the case. If we're in the worst case, and the left half is completely empty, and the right half contains all the elements, because all the elements are bigger than the pivot, then we've only reduced our problem size by 1, and then we run Quicksort again, and then we're still going to have the same problem again. Our pivot's still going to be the smallest element, so we're going to run Quicksort recursively again on an array of size 1, and then on almost the full array, and we're going to keep doing this and keep doing this, which gives us this runtime. It gives us n steps, and then t of 0, t of n minus 1, t of n minus 2, t of n minus 3, etc., because with each recursive call, we're going to only be reducing the size of the problem by 1, and this gives us an n squared runtime. So ideally, we want to find a way to balance Quicksort such that most of the time we get this case, the best case that we had. I may have said average case, it's best case. We want to get this best case version where we balance the 2 halves. And with that, we will finish up for the day. Tomorrow we'll get to a tiny little bit more on Quicksort, and then we'll wrap up for this week before we get to strings for next week, which is very exciting. Finally, we're going to be able to deal with words and not just letters. I will catch you all tomorrow. Thank you very much.